Okay, welcome back. Now, let's take a look at some applications of the canonical ensemble partition function to calculate thermodynamic properties in a simple case. So this is the application of an ideal gas. So what we're looking at is a collection of non-interacting molecules. So let's take a look at how we have set this up. But first of all, let's talk about what the Hamiltonian for this system might begin with and what are the approximations that we're going to make. So if we have a system of n identical molecules saying that each has x atoms in each molecule, then we would write out the Hamiltonian, say, looking something like this. So there would be the first term, which would be the individual molecular contributions, so the translation, rotation, vibrational motion for each of the molecules by themselves. But then we would have the interactions between the molecules showing up as contributions to the Hamiltonian. So here I've added the pairwise intermolecular contributions. So this would be like the van der Waals attractions, repulsions, and things like that. Now, generally what we learned before is that this is an approximation. There could be 3-body, 4-body potentials that you have to include. But for our purposes, we just want to just make sure that we make a clear picture of what you have in the Hamiltonian. Now, the phase space that we're going to describe this system is going to have a dimensionality that's 6 times n times x. N is the number of molecules, x is the number of atoms in each molecule. And in this picture where we have non-interacting molecules, this ideal gas approximation, we can assume that these molecule-molecule interactions can be neglected. So in that case, we can include just this term here, which is just a sum of all the individual molecular contributions where alpha equals 1 to the number of molecules. Okay, and that is this expression down here. Now, if we take that expression and we plug it into our canonical ensemble partition function, then it looks like this. Okay, so remember, it's just the sum with the energy here divided by kBt. So for the energy, we substitute in the Hamiltonian to give us a partition function that's a function of all of the microscopic coordinates, the momentum and positions of our molecules. Now, taking this expression, I've put parentheses here because I want to show you that then this can be turned into a simpler form where we take everything in parentheses and we call this thing in parentheses the molecular canonical ensemble partition function. So this is that partition function, and the canonical ensemble partition function now is just 1 over sigma v, where that is going to be n factorial for gas molecules. And this is a product of all of these molecular canonical ensemble partition functions for the n atoms, n molecules that are in our system. Now, we have to include in this also this sigma term to avoid overcounting indistinguishable molecular orientations in our system here. So for different molecules, if it's an asymmetric molecule, then this is just going to be 1. So there's no indistinguishable orientation. But for molecules like hydrogen, then there are 2 indistinguishable orientations. Same for water. For ammonia, there will be 3 indistinguishable orientations. Ethylene, there's 4. You can work this out later, but methane and benzene both have 12 indistinguishable orientations to them, okay? And since all of our molecules are identical, they're all governed by the same Hamiltonian, then this is going to be the same for every single one of our molecules. So we can actually then write this equation in this form here, where it's just this molecular canonical ensemble partition function raised to the nth power divided by sigma v for indistinguishability in their translational motion. All right, now, when we do this, we're going to take the full phase space, which is 6 times n times x. We're going to call that gamma space. And then we can work with a smaller space, which is the 6x dimensional phase space, which is formed by the positions and momentum of the atoms in the molecule. And that's going to be called mu space. So the molecular canonical ensemble partition function is written over the microstates in mu space, and that's given by this summation here, or if you want to do it, this is in terms of microstates indices, but if you wanted to do it into discrete energies, you can use it here where you have your discrete energy degeneracies there, which you can calculate according to this formula here. If you wanted to go into the classical limit, then you would just replace that integral, this summation with an integral, and this now becomes the density of states for our molecular system. Now, if I focus then on the translation, rotational, vibrational motion, then we remember from those chapters that the translation depends on the momentum, the rotation depends on the angular momentum, and then the vibrational contribution depends on the normal mode coordinates and their derivatives here. So again, this ignores couplings between the molecules, but it also ignores couplings between the different types of motion. So yet another approximation to this picture where you know that there can be rotation and vibrational couplings, but we're ignoring that in this simple picture here. So this approximation now allows us to split our molecular canonical ensemble partition function into just simply a product of the translational contribution, the rotational contribution, and the vibrational contribution. So as long as they remain uncoupled, we can use this approach for separating out the molecular canonical ensemble partition function. And we can also, if we wanted to, we can add the electronic motion and nuclear motion. As we get more advanced in the course, we'll see that we can add additional terms here to account for what's going on inside the atoms. Now, if we take this picture here and we go back to our previous picture here, where we have the canonical ensemble partition function, then we can write down that the canonical ensemble partition function can be written like this for this system of non-interacting molecules where there's no coupling between these different types of motions of a molecule. All right. Now, given that picture, let's take a look at what's called the classical equipartition of energy theorem, where we apply that in more detail for different types of molecules. So if we look at that translational motion contribution, it has this form here, which would be of no surprise. Capital M is the total mass. And here is the rotational contribution, which we learned all about. And here now is the vibrational motion contribution for a molecule with X. This is a nonlinear molecule with X atoms. And what we learn is that all the coordinates here are squared, whether they are position or momentum, and the equipartition of energy theorem tells us that there's going to be an average thermal energy of 1/2 kBt associated with each coordinate that shows up squared in the Hamiltonian. Okay, now that sounds kind of some kind of magical statement here, but we're going to actually show that that is actually true. So every coordinate that shows up squared here is going to lead to a contribution of 1/2 kBt to the thermal energy. So to do that, we'll go back to our molecular canonical partition function, and we will then use some generic form of a Hamiltonian. Remember, we have all these contributions here, but we'll just write it generically like this. So some sum of I equals 1 to m, where x can be some coordinate that gets squared with some multiplier here, which can be generic now. And if we plug that into our expression for the partition function, then you see it looks like this. So I haven't done anything except for just plug this into here in this generic form. And now we see that if there are coordinates here that are not one of these ym's, whether it's position or momentum, then when you do this integral, they will just integrate out to just be some constant out here, and all we'll have left is the integrals involving the ones that showed up in the Hamiltonian, whether that's position or momentum here. So we're left with this integral to do, and all the other ones which didn't have a dependence in the Hamiltonian integrated out to a constant, which is not necessary for what we're going to show here. So then if we go to that integral here, generically we know that that integral works out from minus infinity to infinity. Since we'll take the limits from minus infinity to infinity to this, then we can then substitute for that integral this result, which comes out to be this result here. And there's our molecular canonical ensemble partition function. And we can get the canonical ensemble partition function by just taking that to the n power and dividing by n factorial here, which that eventually will be. And then we get this expression here. Okay. Now, we know we're going to derive the energy from this partition function. So if you remember that expression, we're going to first take the log of the partition function, and taking the log of all of this allows us to split it up into these terms here. And then when we've done that, we can calculate the energy, which is just the derivative of this with respect to temperature. And you can see the only one that depends on temperature is this term here. These guys are not temperature dependent. So now we can just focus on taking the derivative of that with respect to temperature, and that gives us this term right here, which eventually simplifies to this term right here, where now m is our number of terms in the Hamiltonian that show up squared. All right? So now we take that expression, which is here, and then I'll convert this into the number of moles times Avogadro's number, and this becomes the gas constant. So now the energy becomes m/2 nRT for the prediction from the classical equipartition of energy theorem. So every quartic term will give you 1/2 kBt, which you see here. So it's just U over N gives us 1/2 kBt to the mean molecular energy. So in terms of the molar energy then, looking at that expression here, that means that the molar energy is going to be m/2 times RT. Now, to do a comparison with the experiment, we know that the derivative of the energy with respect to temperature is the heat capacity. So this is our prediction for the heat capacity of an ideal gas of molecules where there are m quartic terms in the Hamiltonian. And so we can now check to see how this compares with the experimental heat capacities of gases. So let's start with the simplest case. Let's start with a monatomic gas where we have no rotational motion, no vibrational motion. We just have translational motion. And so the Hamiltonian is just that. So there's 1, 2, 3 quartic terms in the Hamiltonian. So that means that our expression is going to be 3/2 times R. So 3R/2 gives us a prediction of 12.47 joules per mole Kelvin. If I compare that to monatomic gases, then you see that that prediction is pretty much spot on for all of these monatomic gases. So that's quite nice. You think, okay, that makes good sense. Everything seems to be working out according to plan here. So this is a really impressive agreement for such a simple approach, and it works well for these monatomic gases in the ideal gas limit here. Now let's take a look at diatomic molecules. Now, a diatomic molecule is not only going to have translational motion, it's going to have rotational motion and vibrational motion. So we're going to have 3 quartic terms for translation, 2 quartic terms for rotation. Remember, one of those moment of inertia principal components is 0, so that only leaves 2 quartic terms for the rotational motion. And that leaves us with 2 quartic terms for the 1 normal mode vibration in our diatomic molecule. So when you take those all together, the diatomic molecule has m equals 7 quartic terms in its Hamiltonian. So the prediction for that then would be 7R/2 for the heat capacity, which comes out to be 29.10 joules per mole Kelvin. So how does that compare for diatomic molecules? Well, here are the measured heat capacities for a variety of different types of diatomic molecules. And you can see, well, one, it predicts that they should all be the same. They should all be 29.10. And in fact, they are very close to all being the same, but they're not 29.10 joules per mole Kelvin. They're all systematically lower than that, although they are all pretty much the same there. So that's one pro on this, one positive thing is that they're all the same, but they're lower. And in fact, actually, if you look at them, they're all lower by a value of about 1 gas constant. So in other words, one of the R's here, in other words, instead of 7R/2, it's more like 5R/2. And why is that? This really puzzled Boltzmann when he was trying to do this, because he was getting disagreement and he didn't understand what was going on. The classical picture, if you look at this, is that you think about the energy as being sort of thermally equilibrated among all the different types of motion. So you might think about the energy kind of going into the same amount going to each of these different buckets associated with translation, rotation, and vibrational motion. But in fact, actually, if you threw out one of these terms, like the vibrational contribution, you would get a value of 20.74, which is pretty close to agreement for that, but he had no real good explanation of why he had to throw that out. But that was sort of the thought, is that you somehow needed to get rid of the vibrational motion in order to get agreement, but no real understanding of that. Well, that was decades before quantum mechanics, but what we learn when quantum mechanics come along, as we'll learn later, is that the energy is not continuous. Energy actually becomes discrete in quantum mechanics, and so the spacing between the energy levels is what makes some of these contributions appear to be continuous, while other ones are not at all continuous. So translational motion has very small energy spacings in quantum mechanics. Rotational are much wider, much bigger gap than translation, but there's still a significant amount above KBT, below KBT, that it appears to be somewhat continuous, whereas vibration is such a large gap that even at room temperature, you don't have enough energy to excite into these higher levels, and so you lose this contribution. So that's the quantum mechanical picture, explaining why we've lost the vibrational contribution, but we still have yet to understand why quantum mechanics it comes about and why it leads to this kind of result. But that was the reason why Boltzmann did not get good agreement. So if you look at these energy spacings here, then you can see that if this is related to KBT, if you just divide the energy spacing divided by the Boltzmann constant, you come up with a temperature, which we call a characteristic temperature, which can tell you how high of a temperature you need to be before you can approximate, make the classical limit approximation, assume that you don't have to worry about the quantum mechanical quantization of energy levels here. And you can see that for translational motion, the delta E is so small that all you need to be is well above 10 to the minus 8 Kelvin. These are what typical values are before you're in the classical limit. So that wasn't too bad, and that's why the classical contribution for translational motion agreed. If you look at rotation, it can be typically on the order of 10 Kelvin, and so you can be easily at room temperature above this, and that's why you can easily populate these levels, and it appears like a continuum, and you're okay at room temperature to see a lot of the rotational motion contribution to the heat capacity. But on the vibrational side, this characteristic temperature is much higher, and so you have to get to really high temperatures before you start to see that you can excite into these levels as if it was a continuum of energy levels. And so that's why it wasn't seen at room temperature. It wasn't high enough to excite these molecular vibrations. If you look at, say, hydrogen gas, what you see is that if you go to higher temperatures, you can get to the vibrational contribution. So here's the heat capacity of hydrogen gas, and you can see you get to 7/2 R if you get to temperatures well above 1,000 degrees C. But then if you go actually too low, you not only lose the vibration, but you can actually lose the rotational contribution, and then you would drop down to just 3/2 R in that case. So it's the quantum effects that give us this step-like dependence to the heat capacities of gases. Now, what we can do is actually take the same idea and apply it to solids in a very simple example. In solids, different than the gas phase, we have no translational motion, and in fact, actually, we can even assume that there's no rotational motion, only vibrational motion. And no rotational motion is a pretty good assumption if it's not a molecular solid. So if we think about a lot of element metals and things like that, then that's a good approximation. So that leaves only the vibrational motion as the primary place for the energy, the thermal energy to go. And so if we think about the solid as just a bunch of atoms that were connected by springs and all undergoing vibrational motion, we would just apply the equipartition energy theorem and just predict that since there's 3 dimensions, then there's 3 kinetic energy contributions and 3 potential energy contributions for each dimension. That would give us a total of 6/2, or m equals 6, or 6/2 times r, or 3r for the prediction for the heat capacity of a solid, and that gives us a value of 25 joules per mole Kelvin, which is something that's called the Dulong and Petit rule for the heat capacity of solids. And it turns out actually that actually gives you a pretty good prediction at room temperature for a lot of materials. I give you a table here of different elements, and their heat capacities at room temperature. And you can see the prediction of 25 is pretty close to what you see for all of these elements. Now there are a few where it's off, and I highlighted them in red, like beryllium and carbon are much lower and silicon are much lower. So you see that when they're off, they're lower than the predicted value, as you might expect. We're losing contributions. We're not populating the levels like in these ones in red as we do in these other ones. And if you look at them as a function of temperature, you can sort of see that kind of behavior. You can see that diamond, which has a really low value of heat capacity compared to this at room temperature, does eventually start to approach that value of 3R. Same with silicon, and the sort of softer metals or elements will actually approach it even sooner. And so you can see that there is eventually agreement with Dulong-Petit, but some materials require higher temperatures before they agree. So the quantum effects are playing a bigger role in diamond than it is, say, with lead. So I'll leave this question with you. How do you why do these different materials reach the Dulong-Petit limit at different temperatures here? So looking at this plot here, how would you explain that in terms of your understanding of the bonding inside these things and what you might know about vibration and bond strengths and force constants? And that's it for the rest of this chapter.